today is no different. Right now we're actually streaming to my YouTube channel. So if you are sitting here thinking, you know, I would have had it if she would have just said that one more time, you know what? You can hear me say it as many times as you want. Because I had that experience a lot when I took classes, and so this is a resource for you to come back to. If there's anything that you want to hear again, it's on YouTube. So I will be posting links to the videos on the webpage. So the material for this course, there are books. You should all have a book in front of you. If you don't, they're up at the corner of the room. And yes, please sign in and wear your name tag, as Susan has requested. On my website, so my mother named me differently enough that I own the Google. So if you spell my name correctly, Lesa with an E, L-E-S-A, Hoffman, and type that into the search bar, the first like 37 links are me. So you'll find my webpage. On there, there's a heading for talks and workshops, and at the top of the page is the zip folder that has electronic versions of everything that's in front of you. So in addition to the examples and the lecture slides, the electronic packet, which is the download here, has example syntax, data, and output in SAS, SPSS, and Stata, as well as a couple Excel files that show additional calculations that I used in the examples. So you can download all of those resources if you haven't already. And another set of resources I wanted to make sure you're aware of are my regular courses. So I just finished a full-year sequence on longitudinal and multi-level models at the University of Kansas. So if you go to the course materials page, you'll find links to each of those courses, and you will see pretty much all the materials that you have in front of you and a whole lot more, as well as videos for everything. So I figure I work really hard at trying to be a good instructor. I want as many people as possible to benefit from that. So please have at. So if there's any resources that for models, examples, things that you don't see in front of you, let me know, and I'd be happy to point you to a particular example or a class topic on those. All right, so you have on the front page of your packets a syllabus here. The schedule that I had put together is slightly different. I understand that it's not good to sit here for more than like an hour and 15 minutes in a row, tops. People lose their will to live very quickly, including me. So we'll have a break around 10 o'clock, good 20 minutes or so to get outside, thaw out, as it were, refill your coffee. An hour and a half for lunch. I'd like to do that way you have time to decompress or review the lectures as you wish. And then the last part of the day, I'd like to finish whatever we haven't finished, but also give you a chance to ask me questions about your own data. I feel like there's probably a lot in common to the folks in this room in terms of the things they want to know, so it would be useful for each other to benefit from that type of discussion. That being said, please be the person who interrupts me every 5 seconds if you want to be that person and ask questions as I'm going. I know it's intimidating to ask questions in a big room, but it really does help, I think, because chances are you're not the only one with that question. So if I said something that's unclear, or you just want to say, what I think I heard you say is this, and I can confirm or deny, that's totally fine. So let's keep this informal, let's keep it relaxed, let's keep it fun, and let's keep it useful. That's my goal. So that's me and my spiel. Any questions so far? So let me learn a little bit about you. How many of you are primarily SAS users? No one. One couple of people. Primarily SPSS? More people? Stata? More people? R? Lots of R people. How many of you who know R know one of the other packages too? Most people. How many people only know R? A couple of people. Wow. Okay. So I hate to tell you, I'm not an R person. There is something on GitHub that I know about that's another student at the University of Victoria did some of my examples in the book in R and had posted it up there. You might be able to find it. I'll see if I can track it down. Otherwise, hopefully the examples that I have in the software will be enough for you to translate it into your own packages. I teach in SAS because I think it's the most user-friendly. It works for everything in multi-level up to a point of advanced modeling, at which point I switched to M+. But I'm happy to try and translate things as much as I can. I can read R syntax. I'm just not a heavy-duty user. So let's see. I don't think there's anything else. Anything else from your end, or do you want to dive in? Let's dive in. Heck yeah. All right, make sure this is still, we're streaming. Everybody can still hear me? Okay, please let me know if not. Projecting for 8 hours is not in my DNA, so I have the microphone. I can crank it up if I start to drift off here. So, starting from the very beginning here, what is multi-level modeling? So since I can't go around and point at your various screens. Let me see if I can get a pointer option that will work. Here's a laser pointer. There we go. So, what are you here to learn? The term multi-level goes by a lot of synonyms. These are all exactly the same thing. Don't let anyone tell you different. So I like the term multi-level because I feel like it's the most general. I tend to say multi-level models for longitudinal data as the type of thing that we're here to learn about. But if you take this same class in the statistics department, it would be called general linear mixed models, or generalized, where the ized means some kind of not normal distribution. The mixed part comes from the combination of not only fixed effects, which show up in all the models you're used to, but also random effects, which are going to be the new part. These are also called random coefficients models, and hierarchical linear models if you take this class in education. Not to be confused with hierarchical regression, which is a different thing. Special cases that you may have heard of. How many of you have done repeated measures ANOVA before? Lots of people. Guess what? That's a multi-level model already. It's a special case with only a random intercept. If you're here to learn growth curve modeling, we're doing that this afternoon. The term latent can make you sound extra fancy. It is also used to convey that you used SEM software instead of MLM software to do the exact same model. Within-person fluctuation models, such as for ecological momentary assessment, those are models that use these types of, those are data that use these types of models, I should say. The classic case from education, nested or clustered observations like kids in classes and schools and that kind of thing, these models work for that. Cross-classified models or crossed random effects models I can think of are used in two particular areas, one of which we'll talk about tomorrow afternoon. For experimental designs where people respond to the same items, models with crossed random effects such as in psycholinguistics are used for that, and I have an example for that. Also in education, there's a term called value-added models designed to try and look at the incremental contribution of a teacher to student learning. Those same models work for that type of situation. And last but not least, psychometric models. How many of you have had factor analysis or SEM? Lots of people. Guess what? That's a multi-level model too, because a latent factor is the same thing as a random effect. So what you call a factor score, I call a random effect, but it's 6 of one, half dozen of the other. There's a lot of different terminology and different purposes behind measurement modeling, but it is essentially the same thing as a multi-level model. So a framework that I use to understand how these models differ from where you may be starting from. General linear models is usually the first course that people take, and I want to build on that common foundation to explain how these things differ. So the framework that I use is to think about different sides of a model, where one side is the side you're used to thinking about, model for the means. Synonyms for this include the fixed effects, or the structural part of the model, and this is the side that you're used to thinking about in testing hypotheses and answering research questions. It's which predictors go in the model. Do they have main effects or do they have interactions? Do they need nonlinear terms? All of those kinds of decisions are about fixed effects. Each person in your data set would get the same slope for the main effect of your predictor. Everybody gets the same slope for the interaction coefficient. That's what fixed means. It means everybody gets the same. The other side of the model is where the action is. This is how multi-level models differ from regression models. It's what's called the model for the variance, or otherwise known as random effects residuals, or stochastic, where that just means the error part of the model. And this is the part that you're most likely used to making assumptions about rather than thinking about choices. So let me ask you this. In a regression model, you have beta 0 and beta 1 predictor, blah, 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 blah. What's at the end? You write out the regression equation. There's a little letter hanging out there. A residual, E, R maybe. Who put that there? Did anyone ask if you wanted E or R at the end? No, seriously, if you think about it, when you load up your software, you have to tell it which predictor variables to go in, how they're centered or coded, whether they have main effects or interactions. No one asked you about R. You were told that R residuals in regression had to be three things. Do you remember what they are? Normal, normally distributed, homoscedastic, constant variance, and what's the other one? This is the audience participation portion of the program. What's the third one? Don't be shy. Independent, yeah. So you were told these things had to be true or else, right? Or else what? Turns out there's a model for that. If the residuals aren't going to be normal, that's what generalized models are for, like logistic regression or count regression or zero-inflated models and all that kind of stuff. If they're not going to have constant variance, some of that is translated by having a different type of error model, such as non-normal, but some of that is because people change differently over time. So variance will increase or shrink as a function of individual differences in change. That's what random effects are for. And last but not least, the big one, independent, in longitudinal data in particular, that's never going to be true. So we add new kinds of error to the model so that the model then assumes a particular kind of dependency. And whatever kind of dependency is a choice you get to make, and you get to have hypothesis tests as to whether or not that choice is supported by your data. So the idea that we have choices to make in the model for the variance, and that how accurate we are in making those choices dictates how well the fixed effects are going to be trustable, that's the big difference here between regression and any other kind of model. It's choices about the model for the variance. How many kinds of residuals do we have? How are they related to each other? And at any point, it is not necessary to try and fix your data. We do not ever need to transform data. We transform the model instead. So what can MLM do for you? Why should you sit here the rest of the day and quite possibly tomorrow as well? Although now that you know that I'm going to be on the YouTube, we'll see how many of you actually want to come back. So here's my sales pitch. We'll go over each of these benefits in turn. First up, modeling dependency. So dependency sounds like a bad word, right? It sounds like a problem to be solved. Dependency means correlation. It means that observations that come from the same whatever are more related than observations that come from a different whatever. And in this context, we'll say occasions within persons, but within and between are sort of the big picture ideas. And one person's problem to be solved is another person's whole point of the study. Dependency is the entire reason to do longitudinal studies. So we have different solutions for tackling dependency. And you can have fixed effects or random effects. I'm here to talk about random effects mostly, although we'll talk a little bit about the difference. But one thing that you can have to think about, though, is how the dependency is structured given your levels of sampling. So if you have occasions, multiple occasions, and multiple people, you know at a minimum you have 2. If you have multiple people from multiple groups in addition, you have 3. So if people are in the same groups at every occasion, for instance, we would say that those dimensions are nested. So you can think of time within person or time within group in the case of, say, more political science kinds of studies, or trial within person in an experimental design. Those are clearly nested. If you're thinking about your sampling design and you can't figure out which way the nesting goes, what's nested in what, it's not nested, it's crossed. So if I have an experimental design where I have the same subjects respond to the same items, items are not nested in subjects, and subjects are not nested in items. The two are crossed. A trial is nested within a subject, and a trial is nested within an item. So you can have crossed and nested sources of sampling in these models, and you can do it simultaneously. One thing I want to point out about what it means to have a level. Level corresponds to a dimension of sampling in most cases. And whether or not group is a level depends on how many you have. So for instance, if I have a treatment study and I assign my subjects to either control or treatment, I still just have time within person, because once I put in that dummy code for whether they're control or treatment, there's no more group variation that I have to worry about. I have solved it all by differentiating which group is which. In contrast, if I had 5 treatment groups and 5 control groups, then I have to worry about group as another level, because just putting in which is control and which is treatment doesn't control for all the ways the control groups differ from each other and the treatment groups differ from each other still. So then that would be 3 levels of time within person within group in that case. So does that make sense? Seeing head nods? I like head nods. That's always good. All right. Questions? All right. Yeah, go ahead. It's an empirical question whether or not there's any variance that remains after you tell the model which is control and which is treatment. If what you said is true, if the treatment groups all got the exact same treatment, then which group they're in after that should not matter. That's a likelihood ratio test.
But if you know, each of the 5 treatment groups receive just like number of pills of a drug, so is that still can be considered as a boundary level?
It would be, to the extent that group matters. So think about if you have, say, a people study rather than drug study, and you might have treatment groups led by 5 different therapists. Are all therapists equally effective? You hope. It'd be good to know and keep track of that and test.
Oh, then we probably just introduce another factor there is therapy.
Or if you're studying a special population where they're hard to find and you have to go to multiple sites to get enough people, you might have a treatment and control group at each site. Then you have to worry about site differences. And so whether or not you need to worry about it, the extent to which you need to worry about it, I should phrase it as, is an empirical question. But if there are differences between groups that ostensibly should have been the same, that has to be part of the model for the group difference treatment and control to be tested accurately.
I agree with you, and the site should be treated as just like a school or something like that.
Exactly.
Or clinical center, something.
Yes. People who are in groups for reasons other than what you did to them. People who are in naturally occurring groups in that case, especially. Yep. Other questions? All right, let's keep going. So in longitudinal data, there's 3 kinds of dependency that these models primarily are designed to solve. Mean differences across sampling units. So when you do a longitudinal study, some people are going to have better outcomes than others, period. It would have been that way if you'd sampled them once. That's a constant source of dependency that's due to mean differences, and that is represented by what's called a random intercept in our model. It's the idea that each person gets their own mean as a starting point. That is repeated measures ANOVA. There's also individual differences in the effects of predictors. So if you think about time as a predictor, to the extent that people change differently, in addition to their mean differences, that's another way that their observations are going to be dependent. More specifically, when we have individual differences in the effect of time, variance will shrink or expand across time as a result, and observations that are closer together in time are going to be more related. That's another pattern. In these models, we will tackle that pattern with random slopes. For those of you who are less concerned about time and who are doing EMA types of studies, you can think about this analogously as any kind of time-varying predictor. So if I sample, say, stress and physical symptoms every day for a week, to the extent that some people are more reactive to stress, it makes them feel worse when they have more stress in their life. That type of individual tendency is another kind of person-specific dependency. And we treat it the same way with the random slope. We let the model understand that each person needs their own version of a reactivity effect, the link between stress and symptoms. And last but not least, there's this one that I couldn't come up with a better name for, but it's just there. Non-constant within-person correlation for unknown reasons. Observations that are closer together in time are likely to be more related. The end. It doesn't matter whether you're looking at short-term change or long-term change. It's just another pattern of relationship. And so there are features of these models that allow your residuals to take that pattern, even if you don't necessarily have a hypothesis driving it or a reason. So for instance, autoregressive models allow residuals to be correlated in an exponential pattern. Toeplitz models is another one, anti-dependence models, the stuff from the time series literature that you can use to allow a different pattern to your residuals over time that is non-constant, that better matches your data. And the whole reason to pay attention to this is so that the standard errors and the p-values for the fixed effects, the things you actually do care about, so that they're as accurate as possible. The model for the variance is what gives you your standard errors. Your standard errors are what give you your p-values. So it's the inference that you're making about your hypothesis test that depend on getting this part right, even if you don't necessarily care about this part per se. So yeah, I just said that. It's like I knew what was coming. So beyond just getting your inferences right, understanding what kinds of dependency that you have, what sources of variance are in your model, will dictate what kind of model you're going to need to build. So one of the first things that I'll teach you to do is try to assess how much of your variation in your longitudinal outcome is actually cross-sectional. To the extent that most of what you're calling longitudinal is actually cross-sectional, you need cross-sectional predictors to capture it. If, instead, more of your variance is actually longitudinal, you need things that change over time to capture that. So this type of variance partitioning, understanding the sources of dependency and at what level they occur, then will guide your model fitting. So it's a good thing to know just for that sake as well. Number two from my sales pitch here is this idea that models can only have certain kinds of predictors. So in a language that I think needs to just go away and die is this artificial distinction of what we call models based on the type of predictor. So there's still classes at my university on ANOVA as one thing. If you have categorical predictors, it's called ANOVA. Same E as in the regression model, by the way, but just different X's. If you have continuous predictors, it's regression. If you mix the two, sometimes it's ANCOVA, but not if you get interactions, and it's all just general linear models. Those kinds of distinctions about what we label it based on what kind of predictors you have don't exist anymore. These models can allow any kind of predictor. And one thing in particular I want to point out is what happens if you have a time-varying predictor that's continuous. That can't happen in repeated measures ANOVA. There's a covariate box in repeated measures ANOVA that you can use, but they're person-level covariates. They're not time-varying. If you have a time-varying covariate that's continuous, this is where these models can help you, or at least the software for them, I should say. So any predictor at any level pertaining to any dimension of sampling that's in your study, we can incorporate. So labels that we'll use for these, predictors that don't change over time, we call time invariant. Predictors that do change over time are time varying. We may also have higher levels of analysis, such as the site that your people came from, or if you're studying, say, dyadic data, characteristics of the couple as a whole or of the family as a whole. And you can have interactions at the same level or across levels. So you're limited only by your creativity in what you think to collect and then put in your model. Number three, here's the big one. Does not require the same data for every person. So repeated measures ANOVA is a special case of a multi-level model, but it uses a different data structure than what we'll use. It uses something called what I call multivariate or wide, where each variable at each occasion is a separate predictor or variable column. So for instance, here's person 100. Here's their observations at 4 occasions, time 1 through 4. Here's person 101, and here's their observations. Oop, they didn't come the 3rd time. What happens in repeated measures ANOVA, folks? What happens to person 101? Yeah, bye-bye. Because you didn't show up all the time, I can't use you, thanks. That's dissatisfying, isn't it? You should be able to at least keep the data you have. In MLM, we changed the data structure. This is one of the most common misconceptions about MLM, and you will read this phrase in people's results sections and in textbooks. MLM handles missing data. Have you heard this phrase before? When people say handle, it's because they don't know what they're talking about. That's a hand-wavy word, right? It handles it. How does it handle it? I don't know. It just does. No, actually, it doesn't. MLM does not handle missing data. It handles data differently. It works with a different definition of what data are. It works with a stacked data structure. And every software program has an algorithm to do this for you. You never need to do this by yourself, by the way. I've had people try to do that in Excel, and I'm like, no, stop. It takes each row of data, and it transposes each row like, eat. And so each row is an occasion within a person. So in this example, there are 4 rows for each person because there are 4 occasions. The information that is invariant over time, such as their biological sex, gets pasted down across all their rows. You do need to do that. The software will do that for you. Their outcome goes into a new column I've just called Y. And what used to be information contained in the variable names is now its own column for time. So in this data structure, the same rule applies. All rows have to be complete to be included in the model, the same as what we had before. But we've changed what a row means. So now, person 101 will indeed contribute the 3 observations for which the rows are complete. They will not get used in time 3. And all of the MLM software uses maximum likelihood estimation, in which the assumption is that time 3 is no different than the other times that you do have. Basically, once we know which person it was and all of the other information about them, there's nothing special about time 3 that would have changed our conclusions. That's loosely the definition of missing at random, conditionally random. But it's important that you realize the same thing applies, though. Any row that is not complete does not get included. So what would happen, for instance, if person 101 did not tell us what their sex was? Bye-bye. It hasn't been handled. So MLM does not handle missing data. It handles data. 1 row is an outcome, has to be complete. The solutions for what to do about missing data in MLM are not good. There's several choices of not good alternatives. It's an active area of research, and we'll talk more about that tomorrow morning. But the other piece of this here that's important to note is the additional flexibility that switching from thinking about time as discrete choices to a variable in your data set. So how many of you are working with longitudinal data right now or anticipate doing that? Lots of people. How many of you had all of your subjects come exactly when they were supposed to at every single occasion? Anyone? I keep waiting to find someone. One time someone in my class raised their hand, and I was like, really? He did rats. He did animal models with rats. And I kept pressing him, but it turns out even he had this problem, because it turns out if you make rats addicted to meth or cocaine, they up and die on you. That's an outcome. And you know what happens? They get rid of that rat and they go get a new one. So even in animal models, you have missing data or uncooperative animals who up and die on you. And to the extent that the rats that up and die on you, who are more prone to higher levels of addiction are somehow different than the rats that didn't. Wouldn't you want to know about that? Particularly if you're going to apply this to, I don't know, people with different bases for addiction. So even in animal models, this problem happens. And people can be uncooperative in the sense that they don't come when they're supposed to. So well-meaning studies can go awry because people come at off intervals, such as time 0.9. They came a little early. The second time they came a little late, time 1.4, 3.5. When you're thinking about time as discrete, you're like, well, is 3.5, is that time 3 or is that time 4? Like, I don't know which one to stick it in. My answer is don't. Change their time variable to be the actual occasions that you observe them on. That's fine. Time is a continuous variable now. You can have whatever observations for each person that they actually have, and you can build a model around those observations. So the word that I use for that is unbalanced. It's not that this person has missing data per se, it's that they're on a different measurement schedule. Hello, please sign in, grab a name tag and a book. So there's a difference between missing and unbalanced, and we can handle unbalanced data by letting time be whatever it needs to be. Question?
So here the case ID 101 uses 3 cases.
Mm-hmm.
So but the left side, so if there's a missing, so the case 101 will delete completely.
Mm-hmm.
So that's the difference. So use the second data, save a little bit, right?
Yes, the difference also between what people think of as repeated measures ANOVA and MLM is estimation. So repeated measures ANOVA is least squares, and least squares does not have a mechanism for doing something with this observation, whereas maximum likelihood does. And so that's the difference is the data and also the estimation. If you were to estimate a repeated measures ANOVA model using maximum likelihood, you would do it using this framework. And actually, a multi-level model with only a random intercept and time that is treated as a categorical predictor is repeated measures ANOVA. So the difference comes down to estimation and data structure then. Okay. Other questions? All right, then my last part here, you already know how. There's not a whole lot of things that are different. It's just a much higher level of complexity of these models of doing everything at once. So the same concepts that you learned in general linear models, ANOVA and regression, exist in multi-level models. And if you learned generalized linear models like logistic regression, you can run a multi-level version of logistic regression. So here's some more audience participation. Hello, take a name tag, sign in, and a book. How do you interpret an estimate for an intercept? What's an intercept, folks? We're letting the coffee kick in. We're starting low. It's not a trick. I'll start you off. Expected outcome when, when the predictors are 0. That's still what an intercept is. But we're going to have two kinds, fixed and random. Fixed is the part that everybody gets. Random is how you get your own. How do we interpret the slope for a continuous predictor variable? If I told you the slope was 2, could you put 2 in a sentence?
For every one increase in x, you have 2 for y.
That's right. For every 1 unit increase in x, you increase 2 for y. Same here, except we're going to have a fixed slope that everybody gets and a random slope by which that slope can vary over people. The effect of a categorical predictor. So if I have a group difference, that just becomes a jump rather than a slope. We can have fixed and random jumps. And last but not least, a variance component. What's variance? I'll take words or gestures. That's variance to me, right? Yeah. I'm drawing the bell curve. That was the doodle, Google Doodle the other day. Did you see that? Gauss was on the Google. It was a Gaussian thing. Anyway, variance, right? How far off on average is standard deviation? It's the idea that like people differ from each other, that's still going to be the case, but we're going to have more than one kind. We're going to let occasions differ from each other, people differ from each other, groups differ from each other, and so forth. There's just more than one kind simultaneously. So that requires some adjustment in how we think about variance being accounted for instance. You're used to regression thinking about an R-square, right? How much variance did you used to have relative to how much is left over? Well, we're going to have one of those for every kind of variance separately. So it's the same ideas, just an order of complexity higher. Or maybe two. We'll see. But today, for this week, it's just an order. Question in the back? No? Just stretching? All right. Can you still hear me back there? All right then. So more terminology in terms of how to estimate these things. There's a lot of, I think, confusion about what model you're doing based on what software you're using or how you're setting it up. I think about longitudinal models or models in general as logically separate from the software. It's only a question of what all aspects of the model you need and what software program can give it to you most efficiently or least painfully. So I tend to teach longitudinal models from the perspective of multi-level or what we're calling mixed models because it builds most straightforwardly from regression. The syntax looks a lot like regression syntax, and it generalizes more readily to additional levels of sampling and cross dimensions as well as nest dimensions. You can also do many of these models, I'd say most, as a single level structural equation model. So what I'm going to call a random effect, the idea that each person gets their own of one of the model terms, that's the same thing as a latent variable. So the difference in how these things get specified boils down to the data structure again. In SEM, each occasion is a box. So you have to be able to tell your software when the boxes are not the same for each person, when time is unbalanced. I need to be able to say, no, this isn't time 3 for this person, it's time 3.5. In M+, I know there's an option called T-scores that allows you to do that. Does anyone know off the top of their head if there's an analogous option in the software you use? Like an R? Levon? No? No one knows or no one's willing to share? Yeah, so this is the part where it's like, well, you can't do it that way if you have unbalanced data, you need to be able to tell your software about it. In multi-level models, it's a column. So you feed in that column and it understands what time observations you have for each person. In SEM, it's a box. It's an observed variable, so you have to be able to tell it. That being said, if you have multivariate kinds of questions where one outcome predicts the other, if you want to have the intercepts and slopes for change over time of X predict those of Y, can't do that in multi-level software because there's only one column for Y allowed. So then you have to switch to either a structural equation model or what some are calling multi-level structural equation models, a term that drives me insane because most of the time there are no measurement models in there. So they're talking about, say, the between-within side of M+, the MLM side, as multi-level structural equation modeling, whereas I would think of it as multivariate multi-level. Those are nuances we're not going to be able to get to, but I'm giving a workshop at Oklahoma State next week, or 14th and 15th, to talk about that. I also just talked about it in the last week of my 945 class at KU. I just finished this week. Wednesday, I guess, what was that, yesterday, the day before? So if you want to hear more about that, those are the resources for that. So it's not to say that I'm teaching multi-level per se or SEM per se. I'm trying to teach longitudinal. How you estimate it then is a separate question. Any questions on that? Because I know that can be confusing. And this is an area in which, 2 years from now, if I were to talk about this, I may have to talk about it differently given advances in software. It's constantly changing. So what do you need to benefit from this workshop? 2 outcomes from the same sampling unit at a minimum makes it longitudinal. However, I'm here to tell you, if you only have pre-test, post-test, or something like that, you're free to go because I can't help you. There is nothing I can do to make that model more interesting if you have 2 occasions. You can't have random slopes with 2 occasions. If I have 2 dots, there is only one line that connects them. So either I can give each person their own line and say there's no error, or I can give everybody the same line and say there's error, but that's it. You need at least 3 occasions per person to be able to differentiate what is needs their own line from error left over. So in repeated measures ANOVA, there's a box when you go through where they're talking about, what is it, Mari or Mauchly's test of sphericity. You remember this? Yeah, that's fine with 2 occasions. It's always fine. Where that starts to break down is 3 or more. So more data is always better. When people ask me to do power analyses, they say, how many subjects do I need? And I say, more. How many occasions do you need? More, always. The only time I've not said that is when I've had some political science or sociology students that say, well, I have a data set with 30,000 people in it. I'm like, you're good. You don't need any more than that. You might even need less. But in thinking about sample size planning and power, you do have to think about each type of sample, longitudinal, occasions, and cross-sectional persons. So more occasions is better from the perspective of getting a better description of the form of change, particularly if you expect nonlinear trends or if you expect different trends in different phases of a study. Get as many occasions as possible to be able to nail those down. More persons is needed to detect individual differences in change as well as to predict those differences. And the same thing is true for any other dimension of sampling. If I'm doing a psycholinguistic study where I have people responding to words and all of my hypotheses are about differences between words, I need lots and lots of words. Having lots and lots of people isn't going to help you. So it's always a question about what dimension are your predictors in. You need lots of that dimension. Switching to longitudinal or switching to cross models does not solve that problem. So then more vocabulary, picking up into the longitudinal multi-level side of the program. Synonyms. I want you to be able to talk to anyone in any field. And so it's important to recognize when people are talking about the same thing or different things. So I'm talking about longitudinal data on people, but if you have longitudinal data like schools measured over time or countries measured over time, then people are to you. That data they're thinking of? All right, everybody has people? No rats? All people. All right, it's people today then, fine. So between person is the same thing as level 2. This is known more fancily as inter-individual differences, or time invariant. And to the extent that all longitudinal studies start out as cross-sectional studies, you have this one already. This is differences between people that would have been there had you only sampled them once. They're still there when you sample them more than once. Level 1, then, is within persons, intra-individual, or time varying. And this is the new part that only longitudinal studies can give you. So the cool thing about this is that we can test both kinds of hypotheses. Between person relationships are the idea of what is the effect of having more of X than other people on Y. Within persons is the idea of what is the effect of having more of X right now than usual on your Y right now, which is a different thing. So if you think about this in terms of, say, hours of sleep a night, we all have different reference points for what a good night's sleep is, right? I'm one of those people that needs 9 hours or don't talk to me. I'm very jealous of the people who can get by with 5 or 6 hours and be fine. So it's not necessarily that I'm more tired on average than someone who sleeps 6 hours a night unusual, because we're all used to that. But if you take 2 hours away from either of us, look out. Right? That's a purely within-person phenomenon, that if I get less sleep than usual, I am affected more than usual, regardless of what usual is. A question of how much sleep one needs on a regular basis is a separate question. So we get both of these in longitudinal studies, and we can have interactions. Does the effect of getting less sleep than usual depend on how much sleep you usually get? Is there a bigger hit for 2 hours less when it's 7 hours instead of 9 than when it's, or 4 hours instead of 6? So that would be an interaction term of between person by within person sleep. So we got all that going on at once. So synonyms again, level 2, inter, level 1, intra, level 2 is between, level 1 is within. Another way to think about longitudinal data is what the purpose of collecting the longitudinal data was. So on the left side here is a picture of what I would call within-person change, where time is sampled on purpose. You sampled at a rate at which you expect it to be long enough in between occasions that something should have happened. So these are what's known as growth curve models when you're interested in looking at systematic effects of time and how those effects of time differ across individuals. And I will note here, it's always growth curve models. So even if you have straight lines that decline, and you would think that they're like decreasing linear slope models, nope. It's growth, even if it's not curvy. Always growth curves. I didn't make this up, but that's what it's called. On the other side of the continuum are things like daily diary studies or EMA studies, or what used to be called Palm Pilot studies, but that's an antiquated term. Cell phone studies, maybe. Is there a term for that? Maybe you do this? Where's Neon 3? What do you call this stuff now? No? You don't know? You're the only one I name I know, so I have to call on you. But yeah, those kinds of studies where the trajectories for individuals would look like this, where time is just a way to get a lot of within-person information. So we might sample multiple times a day or multiple days or multiple weeks, and there's no effective time. So it's not like, say, if this is stress, you're going to stress them out more as the study goes on by asking them about it. You're just interested in looking at how people fluctuate and how those fluctuations are related within persons across different outcomes. So these models then will have different choices that are going to work for them in terms of time. So for instance, if I put in a fixed effect of time, that's going to not have anything to do with these data, right? There is no effect of time per se. But there may be an effect of time if I think about time differently. So have any of you seen the movie Office Space? I know I'm dating myself a little bit. Yeah, okay, well ask the Google when you get home about Office Space and A Case of the Mondays. And you will watch the clip, right? A Case of the Mondays, right? It may be the case that on Mondays, people have worse outcomes than the rest of the week. That's a time trend. It's not time in study in the same way that would be in a growth model, but it's still a time trend. So you would still want to build in effects like Case of the Mondays so that you can control for whatever time information is relevant before you look at the stuff you care about. And further, it may be the case that a Case of the Mondays needs to be both fixed and random. On average, people might be grumpier on Mondays. That would be fixed, the part that everybody gets. And there may be individual differences in the extent to which Monday sucks for you. That's a random effect. So time is always relevant. The question is just how. And you may have to think creatively in these designs about all the different ways that time may be relevant when it's not the point of the study as it is in growth curve modeling. All right. How are we doing? Any questions or comments thus far? No? Yes? Between person variation to be time varying? Kind of. I would say no, but then I think about the idea of between person differences and a time slope. The time slope itself is time varying, but the extent to which there are between person differences is not. So it becomes a constant trait of the person that they change more or less than other people, but the idea that they change is time varying. Does that help? Yeah, in general I would say no. Between is time invariant, within is time varying. Between is inter, within is intra. I'm going to keep them separate. Between is 2, within is 1. Okay. Other questions? Yes? So this picture is meant to just be like, this is person 1, this is person 2, person 3, person 4. And so what we're going to end up with is an average trajectory for the sample. That would be the fixed effective time. And the extent to which these individual slopes deviate from it is going to be the random effective time. So when you add the fixed and the random back together, you should get the person's trajectory back. And the only data structures in which you can do this is when there's at least 3 points, because you have to have room for variation around the line. Yeah, you can think of it that way. If you were to try and fit a timeline through these data, it would be flat. And so really, we're just looking at the residual fluctuation around the lines. But we do have to think about the idea that people have different cross-sectional levels, right? So this blue person is always higher than everyone else. So what the model will do is fit a different intercept for this person. So there's a line, but it's a line that's up here. And so then we look at sort of what's the difference between the blue person's line and the green person's line. That's a between-person characteristic. Why is blue always higher? What's up with blue? And we put in predictors to explain that. And then from there, why did today suck? Like, what happened today that made this come back down? And so then you have to have time-specific, time-varying information to be able to isolate why today is different than yesterday, because this person was blue the whole time. Does that help? Okay, cool. Other questions? Yes? It depends on how they use it. So there are like clustered sampling algorithms that they're not multi-level models. What they do is try to fit the effects of the predictors and then adjust the residuals so that they take out the effect of the stratification or the cluster, but that's not the same thing. So there are options within most software packages to control for sampling weights and add that kind of thing. In M+ for sure, Stata for sure. SAS has only one level of that possible, I think. But it's a different focus then, because then they're just trying to be like, well, I controlled for stratification. It's done. Versus, I want to know why this sector is different than that sector. Random effects models are designed for the latter. They would allow you to not only quantify how much the sectors are different from each other, but then to predict why they're different with sector-level predictors. So it's a different solution to the same problem. Okay, man in green over here. Yes. Well, who are you? Tell me who you are, and I'll call you your name.
I'm Doug Smith. I'm a social work professor. So if you have a model that does not have growth at all, where you only have one measurement point, but you have nesting across multiple clusters, you can like classrooms. One being taken at one time, and you want to explain variation of known predictors that you might have measured in those classrooms.
Mm-hmm.
How would you refer to that model? Intercepts only, and it's not growth.
I would say that's MLM for clustered observations. Some people would say nested, but nested is a word that means like 17 different things, so I would go with clustered. And in that case, you may end up with random slopes to the extent that your child-level predictors have different effects across schools. That's an empirical question. If you don't have any child-level predictors, then that's not going to happen. But yeah, if everything you care about is school level, but your outcomes are child level, is that the idea?
Yeah.
Okay.
Classroom.
Oh, classroom and student are your levels then. And the outcome you care about is a student level outcome. Yes. So then the only way that a classroom characteristic can predict a student outcome is that it can predict the common variance across students in a classroom. So if you were going to do this old school like slopes as outcomes, how they did it in the 80s before this stuff was invented, they would take a classroom mean of those student level outcomes and they'd stick that as an observed variable in the model, and then your classroom predictors would predict that mean and it would be single level. So conceptually you'd still be doing that. The difference is that by fitting what's going to be a random intercept variance across students that allows students from the same class to be correlated, and it partitions the variance and the outcomes into between classroom and within classroom, then the model understands how many students contributed to each mean, and so it's going to downweight the random intercepts for the classrooms that are less reliable, and it will also downweight them for classrooms that are more discrepant. So that's the idea of shrinkage. The variance that you get would be less than if you computed the classroom means themselves. Does that help?
Yeah, and that's basically the same principle as meta-analysis.
Meta-analysis can be done as a multi-level model, a special case where level 1 is like the people that were in the original studies that you don't have access to, and you approximate their variability with a known constant from the model, like I think they call it W, or like a sampling weight, or it functions as the reverse of a residual variance. And then level 2 is the study level in that case. So yeah, it works similarly because all of your predictors would be level 2 between study things, where you're trying to figure out why some studies had a different effect than others. Okay, man in purple.
You're doing great. It's a lot of fun. When you're talking especially about kind of fluctuations, like CMA kinds of data, how do we think about measurement error here? You know, so what I think I've always struggled with is doing these kinds of CMA fluctuation models. It seems like we're assuming, you know, if the person has 3 time points a day, each is perfectly measured. Never quite wrapped my head around how does measurement error work.
Good question. It is possible to fit what would be truly multi-level structural equation models where you would go back to the item level. So how many items are in the outcomes you would collect every day?
Something of 5 items for a mood measure.
That sounds very reasonable. Multi-level factor analysis of your mood measure, where at the within level would be essentially the residual variance of each item. And so you'd have a within factor that would capture sort of the true score of why today sucks for you, right? It's still the idea of this, I'll use my mouse here, still the idea of this deviation, but it's then been corrected for measurement error to the extent that the observation you're modeling is the common variance across the 5 items. Same thing at level 2. To the extent that for item 1, you gave a high score at each of the times relative to someone else, that becomes a random intercept for the item. And then there's a between factor as well that captures mood differences between people at kind of the aggregate level. So that would be the most proper way to address measurement error. That being said, you better have a lot of people and a lot of days. I've read some simulation studies looking at those models where even when they fit the right model, it didn't work. Like the models that were simpler, that were more wrong, converged more often and more accurately. It was very discouraging. So those types of models, I think, it's an active area of research to what extent small samples can do all of that at the same time. And that's a question that I'm always faced with in the work that I do. We never have large samples, so it's like what compromise is least wrong? One thing that you could potentially do is to do the measurement modeling and output factor scores and then carve up the factor scores into between and within. But there's problems with that as well. So it's a tough question, but these models don't solve any of that. Measurement and trying to decompose truth from error is a whole separate problem. Sorry. Yep, this is the same perfectly measured assumptions as in regression and all the stuff that you learned why that's not a good idea. The exception would be the case that we just talked about, where rather than literally making a classroom mean and assuming that it's perfect, we let the model make it as a random intercept variance, and it understands the data that the mean was composed of. So in theory, that should be better. It's analogous to treating it as a latent variable, where the children are the indicators, essentially, and they're all equally weighted. The loadings would be fixed to 1 in an SEM sense. All right. What else? Who else wants to talk to me? Sir.
So the cursor is the level 2. So if we have the sample size is relatively large, so that means that we have a lot of
No, makes it better. More people makes it better. The extent to which you can find individual differences depends on how many people you have. So, and the extent to which you have power to predict those individual differences depends on how many people you have. More is better. Anybody else? Yes.
So, this is probably a really stupid question, I'm sorry.
I doubt it.
So time 1 and time 2 and time 3, like, do those have to be, like, equal distance, like, and what happens if, like, it isn't? Like, if it's, like, a month apart and then, like, maybe a month and a half or whatever?
Not a stupid question. This is a common thing that I see people do wrong, is they think of it as time 1, 2, 3, and they forget about distances in time. So, no, what you're talking about is a requirement that they're equal interval. That is not the case. You do not need that. Now, that being said, the time predictor you put in the model needs to understand the distances between. Because if you're thinking about the slope of time, it's a 1-unit change of time that the slope is based off of. So if a unit between time 1 and time 2 is a month, but a unit between 2 and 3 is 5 months, then that makes no sense because unit doesn't have a constant meaning. So if you had time where it was 1 month apart and then, say, 5 months apart, I would code that 0, 1, and then 4 so that it's per month, and it understands that there's a 4-unit change between month 1 and month 5, and then I would fit the model that way.
So like 4, like 1, 2, and 3, like you'll have like blanks, kind of like in the data?
There'd be no blanks. You just wouldn't have rows for them.
Okay.
There's no inherent problem with that. The only limitation in that is that you would want to, if you were thinking of fitting any kind of residual structure like autoregressive or topolets, some of those are not appropriate for non-equal interval data, topolets in particular, so you wouldn't be able to use those. But I know that SAS has an option for unbalanced time autoregressive residual structures called a spatial power structure, and there may be something analogous in other programs. So the short answer is no, that's not a problem. Longer is make sure your model understands how far apart the time observations are by the predictor variable that you put in it. Others? All right, then. Should we keep going a little bit? Okay, we'll stop at 10 o'clock. So, transitioning then from the models that you know, general linear models, to multi-level models for longitudinal data. So you've seen this slide before, but to give it a little bit more specific interpretation, model for the means, fixed effects. So I have an example regression model up here. I'm calling it a between-person model. The idea is that this model is trying to predict between-person differences. So this would be appropriate if you have a cross-sectional study. So note the subscripts. They're very important. I used to be someone that never paid attention to these, and now I have seen the error of my ways. Much like flossing, it's one of those things that's like annoying to do, but you better do it. Spent a lot of money on my mouth as a result of not flossing, I'm sad to say. So subscripts are important. We have a Y, and I'm using I for individual. So that way I'm not necessarily saying it's person, but any kind of level 2 unit here it's going to be. So Y for each person. Because each person has a Y, each person has an E. And because each person has a Y and an E, they have an X and a Z and their interaction. So any of the variables that's measured once per person is going to get an I. The betas then convey the regression effects that are fixed effects. And note these betas, this is beta 0 for the intercept, beta 1 for the main effect of X, main effect of Z, and interaction, they don't have I's. That's the big deal here. They are fixed. Everybody gets the same beta 0. Everybody gets the same beta 1. So the relationships between X and Y are fixed. They are sample constant, estimated by the data at hand. The model for the variance, then, is E. E is not a model parameter. E is the idea that the model parameter we're estimating is its variance, and we call this residual variance. So in your output, you never get the E for each person. You could ask for it, but it wouldn't tell you much. Instead, you get its variance. So to write this in more statty terms, these E sub I residuals are supposed to be normally distributed with a mean of 0 because their mean is over here in the red part, the fixed effects, and they have some variance left over. And we can tell how much variance is left over because we know how much variance was in Y to begin with. So we would have total variance, then we have explained variance, and we can talk about R square. So let's one more before we transition. So for example, this is what's called an empty model. This is a term that you would never have used in regression because there's no point. But this is going to be the first thing we do in any multi-level model. So empty means no predictors. Just what it sounds like. So this is an empty model. It has a fixed intercept, and then E is the difference between the fixed intercept and the person's observation. So if I know nothing else about a person, what's my best guess for their outcome? Mean, exactly. Beta 0 is the grand mean. So I'm making a prediction for this person down here. The mean isn't a very good prediction for them, but the mean for this histogram is a mean of 90. Their E is minus 58. And so this beta 0 is the model for the means, and that's where the term comes from. It's literally the mean in this case, but it becomes a conditional mean once we add predictors, in the sense that anybody who has the same X and Z gets the same predicted outcome. So it's a mean, but it's conditional on the predictors. So model for the means is where that term comes from. Model for the variance then, here's the definition of variance, Y minus the predicted Y. So this is all the variance. This is total variance. This is how we compute variance. So moving from that idea then to longitudinal data, let's say that instead of a distribution of cross-sectional data, we have a longitudinal distribution. Here's 3 people, 5 occasions each. Got a blue person who's doing higher than everyone else, yellow person who's sort of mid-range, and purple who's not so good. So we're switching from notation of Y sub I to Y sub Ti for time with an individual. The same rule applies. If I don't know anything, my best guess for your outcome is still the grand mean. So the jumping off point for making predictions about an outcome is the grand mean, which we're going to call the fixed intercept in this model. But I do know something else. I know from which person each observation came. So I can make a better guess by taking the person's mean as my jumping off point. And that idea that each person should get their own mean to start with is going to form the basis of what's called the random intercept. So transitioning from what I call an empty between person model to an empty within person model, meaning adding the within person part, as we do in longitudinal data, we add within person to existing between person. What we're talking about is carving up the variance in Y into 2 sources. Between person variance is the difference here, the differences between the person mean and the grand mean. Why is blue so much higher than yellow, and why is yellow so much higher than purple? I don't know. Characteristics that differentiate persons are going to explain those sources of variance. So the idea of the difference between the grand mean and your mean, that's inter-individual differences. Likewise, after we give each person their own mean, they don't get the same score at every occasion. So the differences of your observation at each occasion relative to your own mean, that's intra-individual variation. So I call this taking Y and making 2 piles. If you are on a job interview and this is your job talk, you are differentiating inter-individual variability from intra-individual variability. That is what you are doing. It sounds better, but it's the same idea. So then to show this graphically, here's an example, say, EMA study where on average there's no change. That's the black line is meant to convey the sample average, and these are some trajectories for different people. Here's a purple person here not doing so well at the bottom. A between-person model would take the residual as the full difference between the grand mean and the person's observation at each occasion. So if I fit a regression model to longitudinal data, the residual at time 1 for this person is this full distance, time 2 is this full distance, time 3, and so on. But this picture shows a violation of one of the basic assumptions of ease in regression. Dependence, right? All the e's can't be negative. That's not how it's supposed to work. They're supposed to have a mean of 0. They're all negative because purple person is below the sample mean all the time. So we fix it. We carve up the error into 2 parts. Each person is now going to get their own deviation from the fixed mean line, the fixed intercept, down to their person mean. And that deviation is going to be denoted as U. U0I, this is a random intercept. U is how I represent random effects. I picked U instead of squiggle or one of the other Greek letters because I can draw U on a board reliably. That is why it is U. U0 is because we're talking about the intercept specifically, so it goes with the idea of beta 0. And I, because each person is going to get their own U0. U0 is how far off your mean is from the grand mean. That covers the dependency in this picture. I have built in a source of dependency that is due to constant mean differences between persons by adding U0, and I'm going to estimate its variance as a model parameter. From there, once I give each person their own mean, E is how far off each occasion is from that person's new mean. And these E's, to the best of my PowerPoint drawing ability, do not have any dependency in them. Some are positive, some are negative, and they have roughly constant variance over time. So then to put those letters back onto our picture, what I'm talking about is separating what we're going to call level 2 random intercept variance. These are the variance of the U0s. U0 is how far off your person mean is from the grand mean. That's between person variance, it's cross-sectional variance, it's inter-individual differences. And then from there, E is how far off each occasion is from the person's mean. That's level 1 within person residual variance. And following other people's notation in the multi-level modeling textbooks I read, I use variance as tau squared for the random effects for the U's and sigma squared for the E's, but I'll always have what it's the variance of as the lower subscript. So level 2 between is random intercept. Level 1 within is residual. Some of the books use the phrase level 2 residual and level 1 residual. I'm not going to do that to you. This is confusing enough as it is. Level 2 will always be random something. Right now it's random intercept only. Level 1 will always be residual variance. So then putting it together, the 2 versions of the empty models would look like this. The model for the means is identical. It's beta 0. The model for the variance is what has changed. So I took what we used to call E, and I split it into how much of E is constant to a person because of person mean differences, that's U0, and how much of E is then left over because of your particular occasion relative to your person mean. And in balanced data that are well behaved, the sum of the U0 variance and the E variance here should equal that of the original E variance. It really is like splitting it into piles. All right. Questions? All right, then it is 10 o'clock. It is time for our first break. So I will see you back here in about 15-20 minutes, somewhere in there.